Today is April 3rd, 2016. My name is Charles Tipton and I'm from the University of Arizona. Today I'm also in the lounge of the senior physiologist here in the convention center. Today I have the privilege and the pleasure of interviewing Dr. Alan Hargens, professor of orthopedic surgery here at the University of California, San Diego, who's also professor of orthopedic surgery at this institution. He is a renowned investigator in the Starling's law of the capillary and has become quite renowned also for his studies in microgravity related to the cardiovascular system, as well as fluid shifts and musculoskeletal system. Today I'm to interview him for the Living History program, and I want to welcome you, Alan, and we're pleased to have you here for an interview, and we hope you're ready for some few questions.
Yeah, so Tip, we've known each other for a long, long time.
That's true.
I think we met in 1979.
That's
when
correct.
You came to UCSD on sabbatical.
That is correct.
Leave. And so it's been a great pleasure to have you as one of my mentors. And from space physiology mentor, I think you are the most important mentor who's guided my career.
Well, I'm pleased to hear that, but you have to work with the product. So let's start with you right now. First of all, you were born in Great Falls, Montana, and I understand that you had a beginning experiences with your father and teachers that led to your becoming a scientist. Do you want to tell us about that at this time?
So when I was growing up in Great Falls, Montana, I really didn't have any interest in science. Oh. My dad was an auditor and a manager in a Farmers Union Grain Terminal Association, and my mom was a nurse at a local hospital. And I think it was some family trips that we made into the Rocky Mountains to go fishing. Those were wonderful times.
Good.
So I think by catching a fish and feeling that jerk on the line, that might have inspired some desire in going forward and learning more about fish.
Well, it certainly had a pretty strong pull. And now, you majored in chemistry, got a BA, I understand, at the University of Minnesota. But what kind of chemistry was it? Was it physical chemistry? Was it biochemistry? Was it organic chemistry or inorganic chemistry?
Yeah, it ended up to be organic chemistry, but along the way I had to take a lot of general chemistry classes. And I think what really got me interested in chemistry was a high school teacher.
Oh.
When I was a junior in high school, I had a really fantastic chemistry teacher, and I think that's what really got me going in terms of chemistry.
Well.
So when I got into the University of Minnesota, I really didn't know which direction I was going, and that's why I was a liberal arts major. But in order to have the option of staying in a chemistry line, I had to take a lot of chemistry classes.
Okay.
So that's how I got eventually into organic chemistry, and I actually got a publication in my senior year in
well, that's pretty
chemistry.
Outstanding. Now, but you also got a PhD in marine biology from Scripps Institute of Oceanography in here in San Diego. Now, how'd that come about, and tell us about that experience.
Okay, so I guess it all started in about the 7th or 8th grade. We were asked to look at various careers, and one of the options was to have a career in oceanography. Oh. So I always kept that in the back of my mind. So when I was a chemistry major, I had a chance to meet up with a world renowned oceanographer. His name was Athelstan Spilhaus, and he was the dean of the Institute of Technology at Minnesota.
Oh, he was, okay.
So I was able to get enough courage to make an appointment with him. And so I asked him, if I want to go to school in oceanography, what is the best graduate school that I can go to? And he said, if you want to spend a lot of time doing research at sea or field research, you should go to Scripps Institution of Oceanography. So that's how I decided to go to Scripps.
Well, you got a PhD in Scripps.
That's right.
And you also became involved with some expeditions. Scripps directed with Alpha Helix, and you went to the Amazon, the Bering Straits, and the Antarctica. So tell us about your experiences on the Alpha Helix and these experiences in the expeditions.
Okay, well, let me start just a little bit to tell you how I got connected with Shoalander.
Oh.
So I started out as a chemistry major when I went to Scripps. I was under the guidance of a young assistant professor. His name was Charles David Keeling.
Okay.
So he made me take a lot more chemistry classes, and I sort of thought, well, I'm here to do oceanography, not to do so much chemistry.
Okay, yeah.
So I, about halfway through the first year, I spoke to some of his more advanced graduate students, and they told me, oh, you don't want to go into this lab. All that Keeling does is measure the CO2 in the ocean, the atmosphere. He puts it into a computer and nothing ever comes out. So one day, again, I got the courage, and I went to speak to Keeling. I said, well, I want to do some more field research and experimental research. So who do you recommend that I go work with? Who would be a good PhD advisor? So he said, okay, let's go down to the Scripps administration office and we'll talk to some of those people. So he and I went down to the administration office, and we ran into a fellow named Andy Benson, who coincidentally, he was one of the discoverers of photosynthesis.
Oh, he was, huh?
Yeah.
Oh.
So Keeling said to Benson, well, Hargens has a pretty good chemistry background. Whose lab would he be good for? And Benson said, well, he should go into Shoalander's lab.
Oh.
And that...
Pete Shoalander.
Pete Shoalander. And Keeling's eyes just opened up like that, because Shoalander was a world-renowned...
Yes, he was.
World-renowned physiologist. He had his own ship, the RV Alpha Helix, his own laboratory and a building, the Physiological Research Laboratory, and he had a lot of support from the National Science Foundation as well. So just by chance, just by that encounter, I was able to get into Shoalander's lab, and that was one of the most, or one of the best things that could ever happen to a young graduate student.
Well, let's go back to the Alpha Helix now. So now you're on an expedition that's going to take you to the Amazon, you're going to go to the Bering Sea and Straits, and then you're going to Antarctica. So tell us about the Alpha Helix and its role and your role in these expeditions.
So I was a young the end of my first year graduate student, and I was assigned to Shoalander's lab. So the first opportunity that I got was to go on the Alpha Helix to the Amazon River. And that was very unusual because Shoalander didn't have a lot of students, so I got to work side by side with him and learn all of the techniques that he had developed previously, and then we also tried to develop a new catheter to measure interstitial fluid pressures in animals.
Okay.
He had previously done a lot of studies on plants to see how they suck the water up out of the ground, and he was able to show that the trees have suction pressures or negative pressures.
You call that sap pressure?
Yeah, that's
Okay.
sap pressure or xylem pressure.
Okay,
So
okay.
those pressures in some plants, like in a desert plant, they need 80 atmospheres negative
Is that
pressure
so?
just
Wow,
to
that's
suck
phenomenal.
water out of the soil. So anyway, we developed this little wick catheter.
Wick means what?
It's like a wick in a lamp.
Oh, okay.
So we put a little wick in the end of the catheter, and the reason is because when you measure interstitial fluid pressure, there isn't a lot of fluid around in the tissue,
Okay.
so you want to increase the contact area between the saline in the catheter and the interstitial fluids. It's not like putting a catheter into your vein or an artery where you have a lot of blood to give you a good pressure response.
Okay, so tell me about your pressures on animals, and which animal gave you the most problem in securing their pressures?
Okay, so we did studies of interstitial pressure on a lot of animals.
Such as what?
Well, we looked at sloths, turtles, frogs, and snakes. And snakes were the most difficult because we had to wrestle with them first. And
How big a snake?
so these were boa constrictors,
Ooh.
and they were maybe 3 meters or
Wow.
longer. And then we had to.
So you
figure
wrestled
out,
with them, actually.
Yeah, we had to wrestle with them, and then we had to get them in a trough so we could tilt them head up and measure their pressures, their interstitial pressures in their neck and down in the tail. And then we tilted them head down and did the same thing to see how much change there was in interstitial pressures when you tilt.
Was there much change?
No, so they have a pretty good regulation.
Oh, that's pretty interesting.
So that was so those snake studies were pretty eye-opening
Yeah, I guess
for
so.
me. I had never handled big snakes like that before.
Now, somehow, maybe you told me that you spent some time on these expeditions living with the Eskimos.
Yeah.
Tell us a little bit about that, and how did you adjust to the Eskimo environment?
Okay, so at the end of the Amazon expedition, Schollander kept talking about the Bering Sea and how wonderful it is to do research in the Bering Sea. So somehow I was able to squeeze myself into the Bering Sea expedition, which was in 1968. And so all the investigators got on the Alpha Helix.
Did you have to get permission from Russia to do that?
No, because we stuck pretty close to Alaska.
Okay.
So we didn't wander into Russian territory. But the Alpha Helix was having problems with the ice. The sea ice was getting into the engine because that's how they cooled the engine on the Alpha Helix, and it was freezing up. So then we had to be towed by an icebreaker.
Okay.
So that wasn't very good. We were sort of, sometimes the Alpha Helix would go off to the right, sometimes it would go off to the left, so it wasn't very good conditions for doing research. So Schollander said, well, you have the option to go over to the shore camp. There was a little shore camp on Nunivak Island.
Okay.
So I flew on a helicopter from the icebreaker over to this little island, and then I was able to get fish that the Eskimos had caught, and these particular fish live close to the ice, so they were in danger of freezing.
Yes.
So I could do a lot of studies and measure their freezing point depression of the blood, and then also measure other things like the colloid osmotic pressure of the blood.
But they are protected, don't they? Seem to be able to resist being frozen by something like equivalent to an antifreeze?
Yeah, so the fishes that live next to the ice have a lot of what's called this glycoprotein.
Yeah, glycoprotein, yeah.
Antifreeze. And so the other fish that live down on the bottom, even though they're at the same temperature, which is about minus 1.9 degrees Celsius, they're not at risk of freezing because they can't be nucleated by the ice.
Oh.
But the ones that are up next to the ice are in serious danger, and they're the ones that have these high amounts of antifreeze.
Well, let's get back to your career. I think near the turn of the century, or between 1987 and 2000, you left San Diego and took a position in NASA Ames with their space program. How did that happen, and what did you actually do when you got there?
Yeah, so that's a really good question. How did I go from marine physiology to space physiology?
Yeah.
So I went by way of orthopedic surgery, if you can believe that.
No, it's kind of hard.
So it just happened, I was doing a postdoc in the microcirculation area at UCSD in the bioengineering department with Ben Zweifach and Bert Fung and Roland Blantz. And so one day, one of the orthopedic residents came to me and he said, well, I hear you have a catheter called the Wick catheter. That was Scott Mubarak, you know.
Yeah,
Scott.
I remember Scott.
So he said, we need a catheter like that to measure intramuscular pressure because there's a condition in orthopedic surgery called a compartment syndrome.
Okay.
So we need a good catheter that has good contact with the tissue fluids so we can diagnose this compartment syndrome. Because it just so happens that compartment syndrome is one of the most litigated situations in orthopedics because
painful.
Yeah, because the orthopedic surgeons are usually focused in on the bones and maybe the other tissues. They're not so alert about the possibility of very high pressures in the muscles.
Okay. But you stayed there for a while, but why did you come back? Didn't you come back to San Diego after your experience? And to be related to post-surgical trauma and rehab, did you learn anything from your experience in NASA that would help you in orthopedics when you came back?
Right. So I had an opportunity when I was on the faculty in orthopedic surgery.
Yeah.
And we had a lot of funding for doing compartment syndrome research.
Yeah, I was the subject in one of your studies.
Yeah. And then also we had an opportunity, well, then we did work on tourniquet design in orthopedic surgery. And the reason was because the orthopedic surgeons were using these narrow tourniquet cuffs. So they had to pressurize these cuffs to 300 or 400 millimeters of mercury to get a bloodless field.
That's incredible.
So what we looked at the pressures, the pressure distributions under those cuffs, and we found that it wasn't very good for compressing the arteries that are deep in next to the bone. So what we did was we redesigned the tourniquets to make them wider, so we got good pressure transmission all the way down to to the artery. And so we could actually cut off the arterial flow and provide a bloodless field for orthopedic surgery at a pressure right around arterial pressure. We didn't have to go up to 300 or 400 millimeters of mercury.
Did you ever use your work with lower body negative pressure I know you did a lot of work at Ames, but did you ever use that concept in orthopedic surgery for post-rehab or any combinations thereof?
Right. So at Ames, I applied for a job to be the head of the space physiology branch.
Okay.
And for some reason they picked me. I still don't understand why.
That was a wise decision.
So after about a year, they decided that they were going to reorganize things. There was a power struggle at Ames. So they assigned me to do more research and also to be the project scientist for the space station centrifuge project. So that freed up a lot of my time, and the project office, the centrifuge project office, said if I devoted half time with them, they would provide a laboratory manager for me and help me recruit other students. So that was a fantastic opportunity. So we had wonderful people in the lab who came in. We had a medical student from Stanford who later became an astronaut. He flew on the shuttle 5 times, for example.
Who was that?
That was Scott Parzynski.
Oh, okay.
And then, so he and I worked on various exercise equipment, and one thing that we developed was an interlimb resistance device where you work one limb against the other, and we actually took that up on a parabolic flight.
Oh, you did?
And then after that, I collaborated with Rob Whalen, and we developed what's called a lower body negative pressure device. And we had already been doing some studies of lower body negative pressure to see how the fluid shift from the upper body down to the lower part of the body. But then we also discovered that you can actually generate body weight with this suction pressure. It works almost like a vacuum cleaner, cleaning up things off of the floor.
Oh.
So you can suck a person's body up to the waist into a chamber and then have them exercise, for example, on a treadmill or maybe a bicycle or stair step or something like that. And that not only gives you a musculoskeletal load, but then it also gives you a fluid shift or a cardiovascular stress. So you can normalize heart rate and other parameters so that they're almost exactly like if you're, for example, running upright on Earth.
Okay.
So with that...
Like in a 1G environment.
Yeah. So we thought that was a good, maybe an early form of artificial gravity that could be used prior to having a centrifuge, a larger centrifuge where you could put people on. And most of these centrifuges are rather short arm, so it's hard to exercise in a normal way because of the Coriolis effects and that sort of thing. So we have tested that device in a lot of bed rest studies, from 5 days up to 60 days. And
60 days, wow.
And we've used that exercise in studies of identical twins where both
tell me about those studies.
Both of the twins are in head down tilt bed rest.
6 degrees, right?
6 degrees, and they can't get up to take a shower. They can't get up to go to the bathroom. They're in that position all the time. So it's really a challenging situation for them. And so we did 8 sets of male identical twins and 7 sets of female identical twins. We had 1 set of older female twins, and you know, when you get old, you can't tolerate things like that. So they they actually quit the study. And
That's
it's
the
a,
best-
it's
only
a
thing you can
challenging
do,
study,
yeah.
especially for
Yeah.
females,
Yeah.
because they have to use a female urinal.
Okay.
So,
Now, you got more on that?
yep.
Okay,
So
go.
just to follow that up, so the negative pressure that we were talking about earlier can be reversed. So if you are exercising in a chamber in an upright posture on earth, you can add pressure or use positive pressure in the chamber and lift the person right up off of the treadmill. And depending on the positive pressure and also the size of that waist seal, you can adjust their body weight to whatever level you want.
Okay.
So we've had people exercising on the moon 1/6 of a G, on Mars 3/8 of a G, or whatever we want. We can just adjust it. And what that's really a benefit for in orthopedic surgery or rehabilitation is you can get somebody within a few days, sometimes even shorter after they've had their surgery, and they can walk. And I had a total hip replacement, and I was able to jog on this treadmill at 1/6 of a G within 1 week after my surgery.
You know, really, lower body negative pressure has really been a tremendous adjunct to rehabilitation in orthopedic surgery then, isn't it?
Yeah, so the lower body negative pressure can be used to maintain the fitness of astronauts in space.
That's right, yeah.
And if you put it on the ground and still use negative pressure, we can exercise people comfortably at 1.4 body weights.
Okay.
Now, if you look at the treadmill that's on the space station right now, they can only exercise comfortably at about 70%
That's what I
body weight.
understand.
So the pressure is a way to comfortably increase or to decrease the weight-bearing exercise. So for patients who've just had like total hip replacement or total knee replacement, they can't go into a swimming pool and exercise because of the risk of infections.
Okay.
But with this pressure device, we can exercise them almost immediately after the surgery.
Now, let's get back to this lower body negative pressure, because I'm under the impression that that method has not been completely utilized in space to the degree that it has the potential. Is that a fair statement?
Yes, and I think the
reason... Why is that?
I think there was an incident at Johnson Space Center where they were exposing a normal volunteer to lower body negative pressure, and they had some sort of a cardiac arrest incident. So then the astronauts heard about that. It even said on the Houston newspaper, "Heart stops at JSC."
Oh,
so
wow.
That scared a lot of people. So
I guess it would.
I think right now there's getting to be more interest in lower body negative pressure, and maybe even lower body negative pressure exercise, especially because it now looks like the fluid shift that goes up to the head, and the astronauts all have these very puffy faces, and they may also have elevated intracranial pressure. So that may be causing some vision impairment. So if they had a device that could move the fluids back down to the legs, like lower body negative pressure, or maybe eventually a centrifuge, that might alleviate that problem.
Yeah, I would hope that the officials at governing space travel would really take a hard look, a better look, a more critical look, because it's quite apparent that the exercise programs that have been utilized to date, at least according to Trappy, have been unsuccessful. So we still don't have a countermeasure that can be utilized effectively for long-distance space flight. So I hope that this will become more of a common feature in future spaceflight. But I also want to mention to our readers or to our listeners that not only this lower body negative pressure work which you've done, you were the first to demonstrate in animals and in humans that a 6-degree head-down tilt did cause a shift in the various compartments of the body, and I hope you'll get the recognition that you deserve for that. But I got to move on to another topic. But do you have any comments
Sure.
to throw that around?
Yeah. Do you remember when I came to Iowa to work with you?
Yes.
Way back in, I think it was around 1980, 1981
Probably, yeah.
or 2, something like that. We tried to measure intracranial pressure in rats during this head-down tail suspension model.
Yeah.
And we tried, but we had difficulty because of bleeding artifacts.
Yeah.
So I think we were at least 35 years ahead of our time, Tip, because right now intracranial pressure and these fluid shifts are considered to be the #1 cause of the vision impairment that the astronauts are getting. So, you know, I think
the vision's impaired on long distance flights, isn't it?
that's right. So, it seems to occur in more astronauts the longer their space flight is.
Now, is it virtually a impairment? They don't go blind, but they can't discern objects, or they can't read, or what is the degree of impairment?
So it primarily affects their nearsighted vision.
Oh, it does?
Yeah.
Oh.
So that's important.
Oh, absolutely. And I also want to mention again that when I was on the decadal study, which is planning 10 years advance for the space community, it was you that brought that finding to our animal and human committee that we needed to study that, because it was an ophthalmologist who discovered that. That was a physician, a flight physician, who realized that astronauts who had been in space for a long time had sight impairment. So this, I think, is a very important finding and an aspect that needs to be really pursued, and I'm glad you're getting funded to do that. Now, I got to get back to the program. And it says here, how did your research area of expertise develop, and who were the many people who influenced your career? You want to answer that, or you want to ignore it?
No, I'd like to answer it, and maybe put it into the context of chronological order.
Okay.
So maybe that high school teacher who sort of inspired me to go into chemistry.
Him, yeah.
He was critical. And then after I got into oceanography, just by chance, meeting in the hallway, I got into doing my first physiology studies. I had never had any physiology before in my undergraduate career.
You had no physiology, and you know, wow, that's impossible.
So just imagine a young graduate student who was working with Scholander doing his first physiology. What an awesome experience that was. So Scholander was a wonderful mentor, and I had wonderful experiences working side by side with him.
Okay.
He was sort of an artist and a scientist at the same time. He
Rare
could
combination.
put together little pieces of equipment.
Well, he invented the Charles gas analyzer. It
That's
shows
right.
how ingenious he was.
Right, right. So he was not only a great scientist, he was a very good machine shop guy who could put things together in a short notice.
Like a mechanism or an instrument maker.
Right.
Yeah.
Right. So I was really lucky to work with him.
Yeah.
And then I got to work under Wayne A. Kison, who is the head of orthopedic surgery, and that's where I met you, and we worked together, and we developed some interest in space physiology way back in 79, 80.
Yeah.
And as you know, we submitted a proposal to have an experiment on the first dedicated space life sciences laboratory.
That's for sure.
And they gave us a little definition phase money, which we could do some experiments on, and we published a paper with Golnick and Mubarak.
CAP.
Yep.
83.
That's right. So A. Kison, I think, was a great mentor.
Oh yeah, he was a wonderful person.
And that's how I got my faculty position at UCSD, my first faculty position, because we got a lot of NIH funding for compartment syndrome and for tourniquet design.
Okay.
And then after that, I consider you to be my mentor
Well, I'm
in
honored
space
to be so considered.
physiology.
I don't think I deserve it, but I'll take it.
Well, no, I think you helped guide me, and we worked very closely together. We've done a lot of things together. We've gone to meetings together, so I think it's been an awesome time with you too, Tip, and I really appreciate
it's been my pleasure.
and treasure that. And
now I see I don't have a whole lot of time left, so I'm going to railroad you with some quick questions.
Yeah.
Okay, you have 300 or more publications, probably 400 is more true than the rest. Of those publications, which one did you take the greatest pride in?
Wow, that's a tough question.
Yeah, I know, it's supposed to be.
Well, it's hard to say right now. So I think there's...
So you're going to pass on it?
Yeah, I'm going to pass on that
I'll
one.
tell you what I think your best study is. I think it was when you did the giraffes and looked at their pressures. I thought that was one of the most creative and inventive comparative physiology studies that's done. So I would vote for that. So let me go to topic number 2.
Okay.
All right. You have 8 patents. How did that ever happen, and which one do you benefit the most from?
Okay.
Financially and professionally.
Okay, so I think professionally, when I got together with the orthopedic surgeons, we patented a clinical Wick catheter technique for compartment syndromes. And we got we sent that through the UC system, and we got some funding from that.
Yeah.
And then one of the orthopedic companies wanted us to sort of refine it a little bit more, so we got a little more money, and we got some research money for that too. And then for the lower body negative pressure, we've always been interested in using pressure chambers either to increase the weight bearing or to decrease the weight bearing. So that particular patent has been taken by Rob Whalen, and he has a company called Alter G now.
He does, wow.
To provide unweighting for, say, for patients or for athletes, so they can rehabilitate sooner.
Right.
But we have some patents with some folks at NASA Langley Research Center for intracranial pressure, for non-invasive intracranial pressure. So those are sort of still in the works, but
wow.
I think maybe NASA will still be interested in
I would hope
these
so. It sounds
non-invasive techniques.
Now, what do you think being in an APS has done for you?
So I consider APS one of my best societies.
Okay.
Because early on I was able to go to the meetings, the FASEB meetings in Atlantic City, and I saw what controversies there were in science. So that was eye-opening to me. And also APS provided funds to young investigators like myself to go to either to the fall meeting or to a gravitational physiology meeting. Those were primarily through Orr Reynolds. So he had a great deal of foresight, I think. So I was very lucky to go to those international meetings because it was very hard to fund that kind of travel off of NIH funding.
I got the idea that you were somewhat surprised, as I was, at the degree of disagreement that occurred in the early APS meetings. Why do you suppose that degree is no longer as present now as it was then?
That's a good point. There seemed to be a lot of controversy about whether interstitial fluid pressure was negative or positive. Most people thought it had to be positive, and some of them didn't even understand what a negative pressure was.
I might have been one of them too.
So I got to see a lot of arguments, for example, between Guyton and Wiederhelm.
Okay.
And over time, I was able to organize a satellite symposium in 1979 of the Second World Congress of Micro Circulation. And out of that satellite symposium, as a part of that satellite symposium, there was a lot of sort of arguing again, but then all of a sudden, about halfway through, there was sort of an agreement that these pressures could be negative. And then there was a lot of interesting discussion between the positive pressure camp and the negative pressure camp, and they were saying that they had held on to their papers for a long time.
Oh my goodness, that's hard to
so
believe.
they wouldn't get published. So I thought that was really interesting, and I was able to edit a book from that meeting, and I think in some ways that started my career in space physiology and our work with you.
Okay.
In that, the chapter 1 in that book, I sort of explored, well, what would happen to the starling pressures in the head and down in the feet when you went into space. So I considered that, and that was about the time you were at UCSD. I think you came right after that meeting. So I considered that sort of the start of my career in space physiology.
All right, this is the last question, and probably the most important, is because it's what advice would you give to a young graduate student in physiology, or wants to be in physiology, to pursue as they look forward to a career in physiology?
Okay. So one thing I learned from Scholander, and I tell my students, is don't believe everything you read in the textbooks.
I think he's probably got a good point.
So often what you find in your experiments don't agree with what's in the textbooks. So rely on your data more than what you're reading in the textbooks. And what also I tell my students is that try to generate some experimental data every day, because you're going to learn new things every time you do an experiment,
Okay.
you have things that you can learn. But from a career standpoint, if somebody is thinking about a career in physiology or any career, I think it's really important to get good mentors throughout your education. That's really important. And to try to select the mentors, try to select the best mentors in the field you want to go into, whether it be in graduate school or in a postdoc. And then just by chance, like what happened to me, I've really had a wonderful career
that's an
in
impressive
physiology.
Career. Mm-hmm. I would also add that find an individual who's interested in you, not what you can do for him, but what you can do for yourself and what you can be for yourself. And if you can find that kind of a advisor, I think you're in good stead. Well, this has been a very interesting and enlightening and informative discussion, Alan. It's been a real pleasure. I hope the listeners will enjoy it as much as I enjoyed it. And thank you so very much for your contributions to our Living History program.
Thank you so much, Tip.